In June 2024, China brought back the first samples ever collected from the far side of the moon. When they cracked open those samples in a clean room in Beijing, the results did not just add to what NASA had found, they contradicted it. The far side's mantle turned out to be dramatically drier than the near side, and its deep chemistry pointed to a mantle so depleted that it challenged the very models NASA had spent decades building. One leading researcher said the findings are turning many of the well-established hypotheses and theories in lunar science upside down. So let's start from the beginning. On May 3, 2024, China launched Chang'e 6. The mission had one objective: land on the far side of the moon, collect samples, and return them to Earth. No nation had ever attempted this. The landing site was carefully chosen. It sat inside the Apollo Basin, a 490-kilometer-wide impact crater nested within a much larger structure called the South Pole Aitken Basin. Now, the South Pole Aitken Basin is enormous. It stretches roughly 2,500 kilometers across. It is the largest, deepest, and oldest known impact basin on the entire moon, and one of the largest confirmed impact structures in the entire solar system. Scientists believe it was formed approximately 4.25 billion years ago when something catastrophic slammed into the lunar surface with an energy estimated to be greater than 1 trillion atomic bombs. But there was a fundamental problem. The far side of the moon never faces Earth. You cannot communicate directly with a spacecraft sitting on the far side. The moon's own body blocks the signal. Radio waves do not bend around a solid object 2,000 miles across. So before Chang'e 6 could even attempt a landing, China had to solve the communication problem first. That solution was a relay satellite called Queqiao 2. The name means magpie bridge, taken from Chinese mythology, where a flock of magpies creates a bridge across the Milky Way to reunite two separated lovers once a year. In a similar way, Queqiao 2 would act as a bridge between the inaccessible far side of the moon and the ground stations on Earth. Queqiao 2 launched on March 20, 2024, aboard a Long March 8 rocket from the same Wenchang spaceport. It carried a 4.2-meter deployable parabolic antenna, one of the largest ever sent beyond Earth orbit. The satellite was placed into a specialized elliptical frozen orbit around the moon, designed so that it could maintain a line of sight with both the far side landing site and Earth for extended periods during each 12-hour orbital pass. This was not a quick relay. Queqiao 2 was built to last at least 8 years and to support not just Chang'e 6 but future missions as well, including Chang'e 7 inches 2026 and Chang'e 8 inches 2028. The satellite also carried 3 scientific payloads of its own, including an energetic neutral atom imager for studying Earth's magnetotail, an extreme ultraviolet camera for observing the plasmasphere, and an experimental radio telescope that could use the 4.2-meter antenna to perform very long baseline interferometry across a baseline of 400,000 kilometers. And alongside Queqiao 2, 2 small experimental satellites called Tiandu 1 and Tiandu 2 were sent into lunar orbit to test technologies for a future constellation of communications and navigation satellites around the moon. With Queqiao 2 inches position and operational, Chang'e 6 was cleared for descent. On June 2, 2024, the lander touched down on a flat basalt plain between the peak ring and the southern rim of the Apollo Basin. The landing site was surrounded by elevated landforms, wrinkle ridges, and a roughly 50-meter diameter impact crater just meters away. The lander had 2 days on the surface. Using a robotic scoop and a drill, it collected material from the top 3 centimeters of regolith across 8 separate scoops, plus a core sample drilled from beneath the surface. The total haul came to 1,935.3 grams, just under 2 kilograms. The samples were sealed in a container, launched into lunar orbit aboard a small ascent vehicle, transferred to an orbiter waiting above, and then sent on a trajectory back to Earth. On June 25, 2024, the return capsule parachuted into a pre-designated landing zone in northern China. For the first time in history, humanity had material from the moon's far side sitting in a laboratory on Earth. The unsealing, dividing, and preparation of the samples took approximately 2 months. The surface-scooped material, about 1,610 grams, made up the bulk of the haul. The remaining 325 grams came from the drill, but a significant portion of that drilled material was stuck to the sample bag and could not be easily removed. The drilled samples were particularly valuable because they represented material from different depths beneath the surface, but processing them required extreme care. Researchers had to divide the core into 1.5 centimeter segments, each representing a distinct depth layer, producing over 100 individual subsamples. That work alone was expected to take an additional 1 to 2 months beyond the initial processing. Meanwhile, in an ultra-clean room at the Institute of Geology and Geophysics at the Chinese Academy of Sciences in Beijing, a separate team began the meticulous work of preparing individual particles for analysis. Samples were sieved, hand-picked, mounted in tin bismuth alloy, polished, and coated with carbon for microscopy. Other particles were embedded in epoxy within narrow tunnels cut into silica glass. Every step followed protocols designed to prevent contamination, because even a trace of terrestrial water or hydrogen on a lunar grain could throw off the measurements that mattered most. And when the science finally began in earnest, the results came fast. When researchers at the Chinese Academy of Sciences began their preliminary examination of the Chang'e 6 samples, the differences from every previous lunar sample were immediately obvious. Under a microscope, the particle sizes showed a bimodal distribution, 2 distinct peaks rather than one smooth curve. The Chang'e 5 samples from the near side had shown a single peak, which is typical of mature, well-weathered lunar soil. This bimodal pattern in the Chang'e 6 material was more similar to the immature soils collected during Apollo 15 and 17, suggesting the material was a mixture. Local basalt blended with freshly ejected debris, probably thrown in from that nearby 50-meter impact crater. In terms of sheer numbers, 95% of the particles had diameters ranging from just over 1 micrometer to about 11 micrometers. Dust level scales, almost nothing larger than a millimeter. This was ancient, finely ground material, pounded by billions of years of micrometeorite impacts. The soil itself was lighter in color than expected, with significantly more white particles, mostly feldspar minerals and glass fragments. The researchers reported that Chang'e 6 soil contained a significantly higher amount of amorphous glass than Chang'e 5, nearly 30% by volume compared to about 21%. The plagioclase content was also notably higher, over 32%, well above the range seen in Apollo mare basalts. The density told another story. The bulk density came in at just under 1 gram per cubic centimeter. The true density was about 3 grams per cubic centimeter. Both values were lower than Chang'e 5 and most Apollo samples. Lower density means more pores, more voids, a looser, fluffier structure. On the Moon's surface, in 1/6 Earth gravity, this material would be even more delicate, almost powder-like, but the chemical composition was where things became genuinely strange. The researchers found that the Chang'e 6 soil was rich in aluminum oxide, about 14%, and calcium oxide, about 12%, but notably lower in iron oxide compared to Chang'e 5 basalt. The trace elements told an even starker story. Uranium came in at roughly 1/4 of a part per million, thorium at just under 1 part per million, potassium at about 0.08%. These are elements that scientists call incompatible because they prefer to remain dissolved in molten rock rather than crystallize into solid minerals. In the near side's Procellarum creep terran, these elements are present at concentrations many times higher. Typical creep basalts carry around 4 parts per million uranium, over 15 parts per million thorium, and 0.5% potassium. The far side's numbers were a fraction of that. The basalt itself was classified as low titanium, low aluminum, and low potassium. And critically, there was almost no olivine, less than 1% by volume. Compare that to Chang'e 5 basalt, which had over 4%. The absence of olivine was not a minor detail. Olivine is one of the first minerals to crystallize from a cooling magma. Its scarcity in the Chang'e 6 basalt spoke to a very different magmatic history, a different kind of source material, a different thermal story unfolding deep beneath the far side's crust. The dominant minerals were pyroxene and plagioclase feldspar, with minor ilmenite. The basalt fragments showed 4 distinct textures under the microscope: vitrophyric, porphyritic, subophytic, and poikilotic, with the poikilotic and subophytic textures being most common. These textures record different cooling rates and crystallization sequences, telling scientists how the magma behaved as it solidified. Mixed in with the local basalt were fragments of something else entirely: breccias, impact-welded rocks containing small pieces of material from the lunar highlands, the white, shiny areas of the moon you can see with the naked eye. These highland fragments included anorthosite, norite, and rare troctolite, materials composed predominantly of calcium-rich plagioclase with minor pyroxene and olivine. They had been flung into the sampling area by ancient impacts and cemented into new rocks over time. The proportion of this non-basaltic material was significantly higher than in the Chang'e 5 samples, estimated at no less than 11% based on the orthopyroxene content alone, and likely higher when accounting for the extra plagioclase. The breccias themselves came in 2 types: regolith breccias, made mainly of basalt fragments, glass beads, and irregular glass shards, sometimes containing anorthositic and noritic material, and impact melt breccias, dominated by single mineral fragments and leucocratic material with almost no glass beads at all and occasional granulite clasts. The 2 types told different stories of different impacts at different times, each one stirring the regolith and adding new ingredients to the surface mixture. Agglutinates, a special form of breccia cemented together by glassy matrix from micrometeorite impacts, made up roughly 20 to 30% of the collected fragments. Their surfaces were covered in glass with well-developed pores, and their interiors contained a complex mix of mineral clasts, lithic fragments, and tiny grains of iron-nickel metal and troilite. These were the products of billions of years of relentless bombardment, the moon's surface being churned and recycled by impacts both large and small. Then there were the glass materials. Rounded glass beads of various colors: black, brownish yellow, white, and green, alongside irregular glass fragments that sometimes still contained remnants of unmelted minerals. These glasses recorded moments of extreme heat, either from volcanic fire fountains or from the searing energy of impact events, each one freezing, a snapshot of conditions that existed for only an instant before the material cooled. As Liu Jianjun, a researcher at the National Astronomical Observatories, put it, the overall petrochemical composition of the Chang'e 6 samples is quite different from Chang'e 5. It shows that the samples taken from the far side of the moon are indeed very different from the near side. Now, here is where the story takes its strangest turn. For decades, scientists believed the moon was essentially bone dry. The prevailing view, built almost entirely on Apollo-era research, held that the moon's interior contained virtually no water. Then, starting in the early 2000s, advances in analytical instruments, particularly a technique called secondary ion mass spectrometry, began to challenge that assumption. Researchers went back to Apollo samples and lunar meteorites with better tools and found water trapped inside volcanic minerals and glass beads. The narrative shifted. The moon was not bone dry, it was relatively wet, at least in some places. But all of those wet measurements came from the near side, specifically from the Procellarum creep terran and thorium, which behaves like water during magmatic processes, both preferring to stay in the melt rather than being incorporated into crystallizing minerals, was concentrated on the near side too. The question lingered. Was the rest of the moon equally wet? Or was the near side an enriched outlier, a chemically unusual province that had been fooling us into thinking the whole moon was wetter than it really is? The Chang'e 6 samples provided the first opportunity to answer that question directly, and the answer was not what most people expected. A team led by Professor Hu Sen at the Institute of Geology and Geophysics at the Chinese Academy of Sciences undertook a painstaking analysis. They sieved through 5 grams of lunar soil, hand-picking 578 individual particles ranging from 1/10 of a millimeter to 1.5 millimeters in size. Of those, about 28% were mere basalt fragments, volcanic rocks derived from the partial melting of the mantle below. These basalt fragments were the primary targets because the water locked inside their minerals would reflect the water content of the mantle source that produced them. The team focused on 2 key indicators. First, a mineral called apatite, the dominant water-bearing mineral in lunar igneous rocks. The apatite grains in the Chang'e 6 basalt were tiny, mostly smaller than 5 micrometers, and present in very small quantities, just 0.07% by volume. Compare that to Chang'e 5 basalt, which had roughly 6 times more apatite. The far side basalt was lean, stripped down, depleted. Second, they examined melt inclusions, tiny droplets of magma that got trapped inside crystals as the rock solidified. These are like time capsules. Once sealed inside a mineral grain, the trapped melt preserves a snapshot of the magma's composition at that moment in time. Some of these inclusions were hosted by olivine, a mineral that crystallizes early in the cooling process. That made them especially valuable because those trapped droplets represented an older, more primitive snapshot of the original magma before degassing and crystallization had altered its chemistry. The measurements were made using a NanoSIMS instrument, capable of analyzing areas just a few micrometers across. The vacuum inside the analysis chamber was maintained at an extraordinarily low pressure to minimize hydrogen contamination from the instrument itself. Every data point was corrected for cosmic ray exposure effects, accumulated over 108 million years of sitting on the lunar surface. The olivine-hosted melt inclusions told the clearest story. They preserved a hydrogen isotope signature close to the expected value for the lunar mantle, largely undisturbed by later degassing. And they pointed to apparent magma with a water content between roughly 15 and 22 micrograms per gram. The apatite told a complementary but more complicated story. Its hydrogen isotope ratios were much heavier, shifted significantly toward deuterium enrichment. This is a telltale signature of degassing, the lighter hydrogen isotope escaping preferentially as the magma lost water in the form of hydrogen gas under the moon's reducing conditions. By the time apatite crystallized, which happens late in the solidification process, the parent magma had already lost between 98 and 99% of its original water. Working backward through the degassing calculations, the researchers estimated the parent magma originally contained somewhere between 55 and 168 micrograms per gram of water. Both methods pointed to the same underlying conclusion. Using the olivine-hosted melt inclusions and the ratio of water to cerium, an element that behaves similarly to water during melting but is not volatile, the team calculated that the mantle source beneath the far side contained roughly 1 to 1.5 micrograms of water per gram of rock. That number matters enormously. The average water content, estimated for the near-side mantle, based on Apollo and Chang'e 5 samples, ranges from about 1 microgram per gram up to 200 micrograms per gram, depending on the location. The median for near-side mare basalts sits around 7.5 micrograms per gram. The far side number lands at the absolute lowest end of that range. The far side mantle is drier, potentially much drier. Not by a small margin, by a factor that could reach 100 or more compared to the wettest near-side sources. As Professor Hugh explained, if the lunar interior on the far side is drier than the near side, it means the water in the lunar mantle may exhibit what scientists call a dichotomous distribution. One hemisphere wet, the other dry. A fundamental split running through the deep interior of the moon itself. And there is another detail that adds a layer of quiet strangeness. Despite the dramatic difference in water abundance between the near side and the far side, the hydrogen isotope composition of the far side mantle appears to be essentially the same as the near side. The ratio of deuterium to regular hydrogen, a chemical fingerprint that traces where water came from, is uniform across both hemispheres. This means that wherever the moon's water originally came from, it had a single, consistent source, delivered at the same time, in the same way, regardless of where it ended up. The isotope signature favors a chondritic origin, meaning the water may have been delivered by the same type of primitive meteoritic material that is thought to have brought water to Earth. This is a significant finding. It means the moon's water is not some random late addition splashed on by different comets hitting different areas. It was baked into the moon early, during or shortly after the formation event itself, and then redistributed unevenly by later processes. Think about what that implies. The amount of water varies dramatically from one hemisphere to the other, but its chemical fingerprint is identical. The water itself has a common origin. Something took that uniform initial supply and split it, concentrating it on one side and stripping it from the other. Whether that something was the South Pole Aitken impact, the crystallization sequence of the magma ocean, or another mechanism entirely, the isotopes cannot tell us. They only tell us that the water was there from the start. The water abundance varies, but its fingerprint does not. That is a clue that runs deep. So what could cause an entire hemisphere of the moon's interior to be drier than the other? There are two leading ideas, and both of them are profound. The first involves the same catastrophic event that created the South Pole Aitken Basin in the first place. That ancient impact, 4.25 billion years ago, released an almost incomprehensible amount of energy. Some scientists believe it may have driven water and other volatile, incompatible elements away from the impact zone and toward the opposite hemisphere. The impact essentially redistributed the moon's interior chemistry, enriching the near side with thorium, potassium, rare earth elements, and water, while simultaneously depleting its hemispheric antipode in the South Pole Aitken Basin. The thorium distribution on the surface supports this interpretation. The near side, covered in ancient impact basins and volcanic flows, has regions rich in thorium. The far side, with its dearth of volcanism, has almost none. And thorium and water behave similarly in magmatic systems, both preferring to remain in molten rock rather than crystallizing into minerals. If the impact drove thorium to one side, it likely drove water to the same side. The second idea is more subtle. It suggests the water distribution might reflect the moon's vertical structure rather than a horizontal split between hemispheres. The Chang'e 6 basalt comes from a mantle source that is extremely depleted in incompatible elements, what geochemists call ultra-depleted. That source may have originated from a deeper layer of the moon. During the cooling of the primordial lunar magma ocean, the deeper and earlier crystallized mantle layers would have been inherently drier than the shallower, later formed layers. This is because incompatible elements like water concentrate in the residual melt as crystallization progresses. The first rock to solidify gets the least water, the last gets the most. Either explanation carries profound implications for how we understand the moon's origin. The dominant theory for how the moon formed is the giant impact hypothesis. About 4.5 billion years ago, a Mars-sized protoplanet, sometimes called Theia, slammed into the young Earth. The collision was unimaginably violent. It liquefied both bodies, sent a massive cascade of superheated debris into orbit, and from that ring of molten rock and vapor, the moon gradually coalesced. The energy involved was so extreme that most volatile elements, including water, should have been boiled away into space. This model predicts that the moon should have been born essentially dry. A drier moon is more consistent with a giant impact origin. The near-side samples had complicated that picture over the past 2 decades. As instruments improved and scientists found more and more water locked in near-side minerals, the water contents turned out to be surprisingly high enough to make some researchers question whether the giant impact model could really account for them. If the moon was born from a cloud of vaporized rock, how did it retain so much water? Some proposed alternative formation scenarios. Others suggested that water was delivered later by comets and asteroids. The debate was open and unresolved, but the Chang'e 6 data from the far side changes the equation. It brings the numbers back down. As Professor Hu put it, modeling results suggest the lunar mantle would have a maximum water content of less than 10 micrograms per gram. The Chang'e 6 estimate of 1 to 1.5 micrograms per gram is consistent with that prediction. If the near side is an enriched outlier rather than the baseline, then the bulk silicate moon, the total mantle considered as a whole, may contain less water than we previously estimated, and that favors the giant impact model. In other words, the far side of the moon may have just rescued the most widely accepted theory of how the moon was born. But the water story, as significant as it is only one of 4 landmark discoveries that came from these samples. The dating work was equally surprising. By analyzing a large number of basalt fragments from the Chang'e 6 soil, researchers determined that 99% of them belong to local basalt that erupted approximately 2.8 billion years ago. But evidence also pointed to an earlier volcanic phase around 4.2 billion years ago. That means the far side of the moon experienced volcanic activity spanning at least 1.4 billion years. That is far longer than anyone had previously assumed for the far side. Before Chang'e 6, our best evidence suggested that lunar volcanism on the far side might have been brief and localized, possibly limited to a single eruptive period. These samples say otherwise. The far side had sustained volcanic activity, 2 distinct eruption phases separated by more than 1 billion years. Something was generating enough heat in the deep interior to drive magma to the surface, repeatedly, over geological timescales, even on a hemisphere that we thought had gone geologically quiet. This was especially puzzling given the ultra-depleted nature of the mantle source. A depleted mantle has fewer heat-producing radioactive elements, less uranium, less thorium, less potassium. These are the elements whose decay generates much of the internal heat that drives volcanism, and yet somehow, even with a depleted mantle, the far side managed to produce lava flows 2.8 billion years ago. The heat had to come from somewhere, perhaps from tidal forces, perhaps from a deeper, less depleted layer, perhaps from processes we have not yet identified. Compare this to the near side. China's Chang'e 5 mission had already demonstrated that near-side volcanism persisted until about 2 billion years ago, pushing the timeline 1 billion years beyond what Apollo had suggested. Now Chang'e 6 shows that far-side volcanism, though different in character and chemistry, also persisted across an immense span of time. The moon was not geologically dead as early as we assumed. Both sides kept erupting in different ways for different reasons, but with a persistence that demands new explanations. Then there is the magnetic field. The moon does not have a global magnetic field today, but it once did. A lunar dynamo, similar in principle to the one that powers Earth's magnetic field through the churning of its liquid iron core, once generated a field around the moon. The conventional view was that this field steadily declined over time until it eventually disappeared. A slow fade, nothing dramatic. The Chang'e 6 samples challenge that narrative. Measurements of paleomagnetic intensities in the basalt fragments revealed something unexpected. Around 2.8 billion years ago, the Moon's magnetic field appears to have experienced a rebound, an increase in intensity after a period of decline. This suggests the lunar dynamo did not fade away smoothly. It fluctuated, it pulsed. The driving power behind the Moon's magnetic field was episodic, not linear. And we do not yet fully understand what could cause such fluctuations in a body as small as the Moon. And finally, the geochemistry of the basalt itself pointed to a mantle source, described as ultra-depleted. This means the rock that melted to produce the Chang'e 6 basalt had extremely low concentrations of incompatible elements. This could mean one of two things. Either the original lunar mantle in that region was simply born with very low levels of these elements, a primordial characteristic, or the massive impact that created the South Pole Aitken Basin melted so much rock and extracted so much material that it actively stripped those elements away, leaving behind a depleted residue. As researcher Yang Wei from the Institute of Geology and Geophysics put it, this depletion could mean either the original lunar mantle was very low in the incompatible elements, or the massive impact event melted the rocks and carried those elements away. Either way, the discovery underscores how profoundly large impacts shaped the deep interior of the Moon, not just its surface, not just its crust, its deep interior. 4 separate studies, all published as cover articles in the journal Nature, all drawn from the same handful of ancient grey dust that Chang'e 6 scooped off the floor of the Apollo Basin. It is worth stepping back for a moment to appreciate the scale of what just happened. For over 50 years, lunar science was built on samples from one side of the Moon. The 6 Apollo missions, the 3 Soviet lunar missions, and China's Chang'e 5, all near side. A total of nearly 383 kilograms of lunar material returned to Earth, and every gram of it from the hemisphere that faces us. Those samples transformed our understanding of the solar system. They gave us the giant impact hypothesis, the concept of the lunar magma ocean, and the late heavy bombardment timeline. But they also created blind spots. We assumed the near side told us about the whole Moon. It did not. Mahesh Anand, a professor at the Open University in the United Kingdom, put it clearly. There are lots of new findings coming out based on the work done on Chang'e 6 samples that are actually turning many of the well-established hypotheses and theories in the field of lunar science upside down, necessitating re-examination of many of those theories. China's Chang'e 5 mission had already shaken things up in 2020 by returning near-side samples that contained evidence of volcanic activity as recently as 2 billion years ago, extending the Moon's volcanic timeline by 1 billion years beyond what Apollo samples had suggested. That discovery was hailed by the international scientific community as changing humanity's understanding of lunar evolution. Chang'e 6 goes further. It does not just extend a timeline. It reveals that the Moon's interior is fundamentally asymmetric. The 2 hemispheres have different water contents, different volcanic histories, different geochemical signatures, different magnetic histories, and possibly different mantle compositions reaching all the way down to the deep interior. The Moon is not one world with one story. It is 2 stories pressed together into one body. And the implications stretch well beyond the Moon. If the giant impact model is correct, then understanding the Moon's composition helps us understand the composition of the early Earth. The Moon is, in a sense, debris from our own planet's violent youth. Every clue locked inside those basalt fragments is also a clue about where we came from. The water content of the lunar mantle tells us something about the water content of the proto-Earth. The chemical dichotomy between hemispheres tells us about the chaos of those first few 100 million years, when the inner solar system was still being assembled through violence. The rare earth element patterns in the Chang'e 6 soil reinforced this strangeness. The total rare earth element content was only about 20 times the chondritic ratio, notably lower than most Apollo samples but higher than some lunar samples. The pattern was relatively flat, with a weak negative europium anomaly. No strong fractionation between light and heavy rare earths. This chemistry was consistent with a source that had been stripped of its enriched components, either by the violence of the South Pole Aitken impact or by the natural process of early lunar differentiation. As Li Chunlai, the deputy chief designer of the mission, said, "The success of China's lunar exploration program is a prime example of the deep integration between science and engineering. The engineering made the science possible, and the science is rewriting what we thought we knew. There is something humbling about all of this. We have stared at the moon for as long as we have been human. We have mapped it, measured it, named its craters, and walked on its surface. We sent 12 astronauts to the near side between 1969 and 1972, and brought back enough rock to fill a few filing cabinets. And for half a century, we believed those filing cabinets told us what we needed to know. Then less than 2 kilograms of dirt from the other side was enough to upend decades of settled science. The sampling so far is limited. One landing site, one basin, one small patch of the far side's vast cratered surface. Whether the drier mantle documented beneath the South Pole Aitken Basin is representative of the entire far side hemisphere, or just a localized feature of that particular region, remains genuinely uncertain. Scientists are careful to note that. We do not know yet. But more is coming. NASA's Artemis program aims to send astronauts to the lunar South Pole region. China's post-Chang'e programs, including Chang'e 7 and Chang'e 8, are scheduled to target the southern edge of the South Pole Aitken Basin as the foundation for what they call the International Lunar Research Station. The Keqiao 2 relay satellite is designed to operate for at least 8 years, standing ready to support those future missions as the communication bridge between Earth and the Moon's hidden face. There is also the matter of timing. Researchers at the Institute of Geology and Geophysics precisely determined that the South Pole Aitken Basin formed 4.25 billion years ago. This date now serves as a critical anchor point for understanding the history of large-scale impacts in the early solar system. Every other impact basin on the Moon and on Mars, on Mercury, on any rocky body in the inner solar system can now be compared against this precisely dated event. It is a reference marker stamped into the geological timeline by one of the most violent collisions in the history of the solar system, and we now know exactly when it happened. And each new sample, each new measurement, each new instrument lowered onto that ancient grey surface will either confirm or complicate the picture that Chang'e 6 has begun to reveal. Li Chunlai, the deputy chief designer of the Chang'e 6 mission, called this discovery humanity's first direct access to key evidence of the deep interior material properties on the far side of the Moon. He said it provides unique information to understand how the Moon's early interior became layered, cooled, and evolved. A crucial step, he said, toward unraveling the mystery behind the dramatic differences between the lunar, near, and far sides. But for now, the mystery remains open. We know the two sides of the Moon are different. We know the far side is drier, more depleted, and geologically stranger than we imagined. We know that something, whether a colossal ancient impact, the slow crystallization of a primordial magma ocean, or some process we have not yet considered, split the Moon's interior into two distinct chemical worlds. What we do not know is which explanation is correct, or whether the real answer is something else entirely, something still buried in the regolith, waiting for the next scoop, the next drill, the next pair of hands to reach down and pick it up. Consider what we have learned in just the past few years. Chang'e 5 showed us the Moon was volcanically active 1 billion years longer than we thought. Chang'e 6 showed us the far side mantle is drier than we assumed. The magnetic field fluctuated rather than faded. Volcanic activity on the far side spanned over 1 billion years. And the deep mantle beneath the South Pole Aitken Basin is chemically ultra-depleted. 4 cover articles in Nature from a single scoop of dirt. Imagine what the next scoop might reveal. And that is what makes the Moon so compelling. After 50 years of samples and 6 decades of exploration, after hundreds of kilograms of rock and thousands of published papers, it is still surprising us. Still hiding things on its far side, still forcing us to ask questions we thought we had already answered. The more we study it, the stranger it becomes. This documentary presents an exploration of scientific discovery and observation, not sensational news. All claims are grounded in peer-reviewed research published in Nature and data from the Chang'e 6 mission. Where evidence is preliminary or interpretation remains open, this is noted explicitly. The narrator's role is to present the evidence, highlight the mystery, and leave interpretation open, exactly as science demands. What we know so far. Here is what the data suggests. Some researchers believe. Others argue this interpretation. What if? Unverified theories are never presented as fact.